Right, welcome back. Hopefully this is one of our final weeks doing this online, but sure, look. Anyway, let's get stuck in. So before midterm, we finished off the folding part of folding and faulting. So just to remind you, we're doing deformation. Deformation means how the crust becomes deformed or changed, and it becomes deformed or changed through two processes, folding and faulting. We pretty much covered all of the folding stuff. A few of you still owe me a bit of work. That was the summary or the flashcards on the sample answer on the distribution of fold mountains. So I will come looking for that. So today we're going to move on to faulting, and what we're going to start off with is just a reminder of the three processes of deformation, which we looked at the very start, because they are key to understanding faulting. Alright, so get rid of myself. So just remember that faulting will only occur when rocks are under extreme pressure. So rocks are elastic, they can withstand pressure up to a certain point, but after that they'll fracture. And it's a fault, a fracture or crack is known as a fault when there's movement on either side of the fault, and that movement can be vertical. Hang on, I'll get myself back up again for the vertical and horizontal. This is very slow today. Okay, so movement along the fault. So this bit here is the crack. Movement along the fault can be vertical, it can be down or up relative to the piece of land, or movement along the fault can be horizontal, right side by side. But if there's no movement along the fault, then it's not a fault, it's just a fracture. Now, let's go again. Alright, so let's see. Okay, so in terms of faulting, I need to go back here. We're just going to recap this. The three processes of deformation. So these are the three ways in which the crust can become deformed. First way is compression, and remember this happens at convergent plate boundaries where the crust is squashed and squeezed. The second one is extension. That will happen at divergent plate boundaries where the crust is stretched outwards and it thins and weakens. And the last one there is shearing. And this will happen at transform plate boundaries where the crust gets torn as the plates slide past each other. Now, out of all of these, only one of them results in folding, okay? So this is the only one here where folding happens. But faulting will happen at all three, okay? So in the case of compression, when compressional forces begin, it will cause the crust to fold, but if they continue, it will cause the crust to fault. If you think back to the fold types, and an overfold becomes an over thrust fold, at that point there we've got faulting. Alright, so just to note here that faulting happens because of all three processes of deformation. Alright, now there's different types of faults. Hang on, how do I get this fella off the pen? We don't want it on pen anymore. There's four different types of faults, each of them associated with one of these processes, and we're going to go through these. And all I want to look at this morning are normal faults, just to get started. So the first one are normal faults. The process which results in normal faults is extension. So these happen when the crust is stretched and thinned at divergent plate boundaries. Second type of fault is the opposite. That's why it's called reverse, because it's the reverse of a normal fault. This happens at because of compressional forces at convergent plate boundaries. The third one there is just another step on from the reverse fault, and that'll make more sense if we look at it. And that also happens because of compression. And the final one then is a tear fault that happens because of shearing at a transform plate boundary. So we're going to go through each of these. We're going to look at how they occur, but more importantly, we're going to look at the landscapes that are associated with them, because the types of questions that focus on this want you to be able to discuss how faulting impacts on the landscape. So each of these will result in different types of landscapes. We'll start off with normal faults. So this is kind of like the before picture up here. So in a normal fault, if you just pay attention to the movement of the arrows here, it's a divergent plate boundary, so that the crust has been stretched and it's been thinned, and when you stretch and thin it, it's going to cause the rocks to weaken, and we get a fault line there. And in this case here's the fault. What happens next then is that there's movement, vertical movement, and in this case the vertical movement is downward and the land here slips down. This is why these are also known as dip slip faults, okay? And what happens when this section of land moves down is it leaves this kind of steep cliff-like face on the landscape, and that's referred to as an escarpment or as a fault scarp. A good example of an Irish one of these is in Kingscourt in County Cavan. So this is the diagram that needs to go into your booklets on page 21. So it's a normal fault, also known as a dip-slip fault. The reason why we show the rock layers is so you can imagine that this used to be inlined. So obviously the orange is with the orange and the purple is with the purple. And to make sure that you put in the directional arrows for the plate movement, indicating it's a divergent plate boundary. So the process is extension. So it gets pulled apart, you get a fault forming here, and this block of land moves down. Now, these two blocks of land then are given a name. The block of land that doesn't move is referred to as the footwall block, and the block of land that moves down is called a hanging wall block. And just to note that it's vertical downward movement, and you need to know the name for this section of land here, which is the fault scarp or the escarpment. Now, if you have a look at this in the landscape, they can be quite difficult to recognize, but if we take a look at this bit here, so this here would be the footwall block. So all of this land here originally would have been up at the same height as this. What you're looking at here, again, so this area here, okay, that equates to the fault scarp down here. And this pen really doesn't want to work today, so let's use the mouse. Oh, and everything has gone black. Well, that's not much use. Hang on a minute. Pause this and get myself sorted. Okay, so basically what I was saying was is this steep cliff here that you can see in the landscape equates to this fault scarp down here. Alright, this block of land up here is the footwall block, and this block of land down here is the hanging wall block. So this moved downwards. Alright, you'd never be given an image like this, it's too difficult to recognize. Here's another example. Let's get rid of all the scribbles. Oh, okay, there we go. So you can see clearly here we've got the fault scarp. Okay, gone down here. There's a man standing on top. This is the footwall block here, and this will be the hanging wall block here. And then over here we've got a smaller normal fault where we've got the scarp there. This block of land here is the footwall block, and this block of land here is the block that moved down, and that is the hanging wall block. Okay, so normal faults as a result of extension of divergent plate boundaries causing one section of the land to move vertically downwards, in some cases upwards, but we'll just leave it downwards at the moment. And I have a very simple video clip here which will demonstrate normal faulting. Okay, here we go. There's about to be an earthquake. Oh wait, nothing happened. Let's try that again. Oh, that's better. Okay. Don't know why that didn't happen the first time around. Alright, so here is the fault scarp, hanging wall block, vertical movement downwards, footwall block. Okay, so all of that detail needs to go onto your diagram. Okay, so once you're able to identify and draw a diagram of a normal fault, the next thing that we need to look at is look at the landscapes that result from it. And this will be familiar to you from the very first thing that we did in plate tectonics. So in this case here, this demonstrates what happens when there's two normal faults parallel to each other. So here's a normal fault here, and here's a normal fault here. And the block of land between them has slipped downwards because the crust is continuing to pull apart and be stretched. When this block of land sinks downwards, it forms a rift valley, and we talked about these quite distinctive shapes. So on either side of the rift valley, we said before, but we didn't use the word fault scarp, but there's very steep slopes. So you've got steep slopes leading down, and you've got a very flat valley floor. And the fault lines themselves, they might even be hundreds of kilometers apart. And your case study for this is the East Africa Rift Valley. And if you think back, you remember this started because of a hotspot beneath the crust, and that hotspot caused the land above to dome upwards and stretch, and then develop faults in there, particularly parallel faults. the other thing then, if you've got a series of these normal faults, so here we have a normal fault here, normal fault, normal fault, normal fault, and if you just check along here, you'll see that the arrows indicate we're at a divergent plate boundaries. So you can get this happening all across a block of land, where you have a section that dips down and another section that dips down, and in between you've got these upland areas. So this is referred to as a horst and graben landscape, and the horst are actually called block mountains. So these remain as mountains in the landscape, but they're not formed in the traditional way mountains will be formed, either volcanic mountains or fold mountains. They're just land that has been left upland. So these are known as horst or block mountains, and then the valleys that sink between them are referred to as rift valleys or the graben. So they can occur singularly, like we saw in this slide here, or they can occur side by side across a landscape, and this is referred to as a horst and graben landscape. So at this point what we're going to do is just remind ourselves what happened for the case study in the East African Rift Valley. And this is a satellite image taken of it, and you can very clearly see the fault scarps or the escarpments on either side. The East African Rift Valley is one of the world's largest fractures. If you think back, when it goes from the Red Sea in the north down as far as Mozambique in the south, and it forms a rift that's almost 6,000 kilometers long. It's been forming for the last 30 to 40 million years, and the reason for that is because of the hotspot. So we have a look at this here and have a look at the key. So first of all, the green is the Rift Valley area. So you can see there's a number of rifts here, and eventually they will all join together to become one rift. And you remember we said that this section here will break away from the African plate. This will become the Somalian plate, and this will become known as the Nubian plate. So basically what we're saying is that there's hotspots beneath the crust here, and these hotspots are pushing the crust upwards, and they're causing the crust to dome upwards, and because of this, the crust is stretching and thinning, and the extension of the crust then results in these long parallel fault lines, and these are normal faults. The crust between the fault lines is about 40 to 60 kilometers wide, and the blocks of land then sink down and they form the graben or the rift valleys. The edges of the escarpment then are marked by these fault scarps, and these can be very, very high. Some of them are up to 9,000 feet high. And also if you look back here, you'll see that we've lakes opening up along the rift, and this is because in some cases the rift valleys have dropped below sea level, and the deepest lake here would be this one, Lake Tanganyika. And if you think back to what we said about the Red Sea was originally a rift valley. It dropped below sea level and is now a fully fledged sea with oceanic crust being formed at the bottom of it. Because there's a hotspot beneath this area here, then some of the magma will escape up at the faults and will form mountains. And again, this is all just revision because we did this in plate tectonics, and we used the example of Kilimanjaro and Mount Kenya. It's still continuing to widen. It's widening at a rate about 2 centimeters, well, not even, we'll say about 1 centimeter, 4 millimeters per year. And eventually the end result of this will be that this section of land falls off, and doesn't fall off, it splits off from the rest of the African continental plate and will become the Somalian plate. Well, probably won't happen for another 10 million years or so. Okay. This is an example of rift valleys and tear faults in Ireland and Scotland. So there's a Scottish rift valley that continues all the way into Ireland, and you'll see Lough Neagh is part of that. So Lough Neagh is just one area where the landscape has dropped below sea level, and that formed there. And we have the Nairn Fault further up, that's part of the Great Glen Fault. So a lot of the faults that we have in Ireland are extension of faults that would have run through the UK. And this is, so here is the Great Glen Fault in Scotland. Here's a picture of it here. So again, you can see it's kind of got that rift shape with the scarp edges and the flat valley floor. And Lough Neagh, just spoke about that. Why is that there? Don't know. Okay, look. Oh yeah, that's because that's the diagram that goes on your notes. So that's enough chatter out of me for the moment. What I want you to do then is I want you to, let me see what page you're at. I want you to read through that on page 21, and do the diagram on page 21 and just recap. Oh sorry, it goes on to a little bit of page 22 as well, and I also want you to recap the East African Rift Valley case study that is on page 26. And I think we'll just leave it at that. We'll start nice and easy. Might be no harm if you go back and have a look at your notes on plate tectonics, and particularly have a look at the diagram that you did for the formation of rift valleys, because that will help you with that a little bit. All right, that is it.